Gerda involves 40 kilograms of 86% enriched germanium-76 at ground Sasso. The other was the Majorana demonstrator, about the same mass, in the SURF laboratory in the United States. So these measurements are in progress. Neither of them has reported the observation. I'm going to go through this fairly quickly because I don't want to take too much time on this. But these are extensive measurements, they're large-scale measurements, and they're not done by dummies. These people have thought of a lot of different things in order to make this measurement possible. They use germanium detectors. The one in Gerda uses argon shielding and argon for cooling. The one in the United States, the Majorana demonstrator, uses electroformed copper and for shielding and for support. Let's see. Let me not say anything more about that. Now let me just say something about this. Germanium-76 has a lot of advantages. Germanium, again, is the source and the detector. Elemental germanium maximizes the source to total mass ratio. We already said that germanium is a good detector. Let's not worry about that, worry about that, worry about that. Excellent energy resolution. That's important because we like to look for this signal over a very small energy range, so the higher the resolution, and germanium has essentially the best resolution of any material that we would use for these measurements. Background rejection, that's something I want to refer to and want to talk a little bit more about. And the technology for producing germanium detectors is very good. And it's interesting, one of the big contributors to the technology is the things that John has worked on through the years and others have worked on, gamma ray spectroscopy. Because it was pretty clear that germanium was going to be the future, so the detector technology has been developed to a fairly high degree. Okay, the matrix element I don't want to worry about. This I'll pass. Okay, let me go to the positive result. And this is the KKDC given by the basis of the authors of this paper. This paper was published in, I think, 2004. And this shows the spectrum of their observation of the peak. Remember, the energy of that was 2039 keV. So this is the peak that they attributed to the double beta decay. This is a pulse-shaped selected spectrum, and it looks fairly convincing. This again is the same measurement, and you can see that there's a Monte Carlo simulation, and it looks fairly convincing. The problem is, others have not been able to reproduce that result, and in fact, the limits that have been set, they essentially say that it cannot be correct. So, the measurements continue, and we, as we said, are going to have a real sensitivity to the signal to background in these measurements. Now, what's going to produce background in these measurements? Well, there are various things, natural radioactivity in the germanium, or in the electroformed copper, or in the argon. There are all kinds of places where we can get background. So we'd like to do everything that you can do in these measurements to reduce the background. And for the next generation of measurements, the number that I heard last week at the talk was that they need to get down to 1/10 of a count per ton year in the region of interest. That's very difficult, okay? But you need to do everything you can to reduce the backgrounds. So that means they need to lower the backgrounds by about a factor of 100 from where they are now. Now, you don't have to eliminate all events in the detector. It's only in that region around 2039 keV. And one source of background is neutrons. Neutrons can arise from two different sources primarily. One is from cosmic ray muon-induced backgrounds. You can decrease those by putting the experiment deep underground. And this is the approach that's been taken. You have to have it underground. You can also get neutrons from natural radioactivity on light elements, alpha particles. And so I don't like to show these kind of spectra because the backgrounds in terms of the neutrons frequently are determined by the construction, the materials, the laboratory, and where it is. Okay, well, there is a lot of concern raised about this particular level in germanium-76. This is the 69th level in that nucleus. Yes, John. The 69th level, and you can see that the energy of it is shown here, and you can see that it decays with a gamma ray of 2040 keV. That was determined by a measurement almost 45 years ago. And so this is right at the energy as to where you would expect that signal for neutrinoless double beta decay. We just happened to have some germanium-76, and we did an N prime gamma measurement on that germanium-76 to see what the region around 2039 keV looks like. And the energy of the neutrons we used was 3.7 MeV. Here is where that 69th level decay would occur. Okay, it's not exactly what we see. We see, of course, a gamma ray that is, oops. We see a gamma ray that is at 2038 keV, and here is the excitation function of that gamma ray, which would argue that there should be a level at about 3.2 MeV that's emitting that gamma ray. This is lower than the other level that people are concerned about, and that's bad news, because the lower the level, the larger the cross-section. And so this is the gamma ray that we observed. We said there must be a level at this energy. If there is a level at this energy, we would expect to see this gamma ray also. So we look in our spectra, and there is exactly that gamma ray that we would expect. So we establish a new level that emits a gamma ray at exactly the same energy as what you would expect for double beta decay. You're shaking your head. You don't believe it, or you're just concerned with the measurement?
No, I'm just saying it's unfortunate.
It's not only unfortunate, it could kill the whole experiment. They should be concerned about it. Now, we published this result a couple of months ago. I don't know how the people well, I talked to some of the people in the Majorana measurement. I think they're a little bit in denial at the moment. It's a real problem. Yes?
But probably, if this is coming, if you know very well the branching, you can subtract.
That's a fantastic idea. So you do 5 years of measurement and you get 2 events. How do you subtract? It is a problem. But they should be aware of these problems. Now, how are they going to get around this? Well, if they can eliminate neutrons. This means you go as deep in the Earth as you can. You have muon shields, and you can, I think, get rid of about 95% of the muon-induced neutrons by that. What else? If you can do tracking. Tracking is important in these detectors. And, of course, the people in things like Agatha and Gratina have pioneered tracking in germanium. What else can you do? Position resolution, again, of course, you need. If you can determine that this occurs in a single event, that's important. Because the 2 beta particles are not going to have very large range. Okay? Now, they do have a little bit larger range than you would hope, so you can occasionally get fooled. You can also get the case where a gamma ray comes in and produced by a neutron interaction, and it deposits all of its energy in 1 pixel. That's possible at some level. We've calculated that. You have a question, Maria?
Well, I think in Gran Sasso they have a muon detector on the top of the mountain, so there you can of course do correlations
Yeah.
on skip events.
But it's difficult. It's difficult. And this just adds to the problems, I'm afraid. Okay,
Is there another candidate to try other than Germanium 76?
I'm glad you asked that.
He has seen the talk.
You're primed to
How,
ask that
how about Xenon 136? Xenon 136 should decay by neutrinoless double beta decay to barium 136. The 2-neutrino process has a lifetime of 2 times 10 to the 21st years, and the lifetime limit for this process is greater than 1.6 times 10 to the 25th years. This is just the same diagram I showed earlier. Here is Xenon 136. It, of course, cannot decay to cesium 136, so it has to decay to barium 136, either by this process or this process. Okay? Now, you've got the same set of problems again, okay? Only a little bit different. The enriched Xenon Observatory, EXO, has about 200 kilograms of liquid xenon. It's 80.6% enriched in Xenon 136 and about 20% in Xenon 134. It would be, of course, be better to get more highly enriched material. The Q value is 2458 keV, very accurately measured. These are just some pictures of it. We've talked to people from the EXO collaboration. One of them visited us for a week just to get an idea of what their problems were and what we might contribute. Just to give you an idea of what the spectrum, now this is not a spectrum of Xenon 136 2-neutrino decay. This is just a calibration spectrum, but it shows that the full width of half maximum of this peak is about 100 keV. Remember, in germanium it was about 4 keV, so this has a energy resolution problem. They tell me that they can get down to about 25 keV. They also do tracking, okay, and a number of other things. So we did similar measurements at the University of Kentucky. We inelastically scattered neutrons from, this is xenon difluoride, and we had solid samples of xenon 130, 132, 134, and 136. I should say something about xenon difluoride because it is a solid material. People, when I talk about it and point out that we've used it in neutron scattering measurements, they quickly ask, can we have some of it for a target? You don't want to have anything to do with it. It reacts with air, it reacts with water. Put it in a vacuum, it sublimes. Okay? So it's fine as long as you keep it in a Teflon vial. You can see the crystals of it here. And so we can determine all of these different things. And so we did scattering measurements on this Xenon 136 sample and the 134. And let me just show you a measurement from Xenon 134. This I showed earlier, so we won't worry about that. Oh yeah, we found a new level of 2485 keV. You remember the Q value was 2458, okay? Not to be confused. And we see 3 decays from this level. I show the excitation functions for each of them. Show the angular distributions from each of them. So that is what this new level looks like. Okay, we even measured the lifetime of it. But anyway, you can see that if this gamma ray is 2485, you could also have in coincidence this gamma ray and this one not shown. You could have this gamma ray and this one not shown. The energy of the level that level is going to contribute to a xenon detector is 2485 keV. And here is the gamma ray. Okay. Now what I've done here is I've taken our experimental resolution and made it 100 kilovolts wide. Okay. Basically to replicate what they would see in a xenon neutrinoless double beta decay measurement. Here is the Q value. Obviously it's going to overlap. So this again creates a background problem for that measurement.
Oh, you will be very famous.
What?
You are killing all these experiments.
It's not our plan. We're planning to help these people. Okay. So the Q value is 2458. We have done a cross-section measurement so we can tell them what the cross-section is for particular energy of incidental neutrons. So let me conclude by saying that measurements of nuclear level characteristics can play an important role in other areas. I've shown 2 examples of neutrinoless double beta decay that we feel that we're contributing. And contributing is telling people what problems they have before they get halfway through an experiment and decide that it's not going to work. Inelastic neutron scattering can really provide a lot of information with other reactions, but you need to look at the total